Hello and welcome. Today, we're going to tackle a topic that's a real headache for a lot of physics students, moment of inertia. But what if I told you that you don't actually need to memorize that huge list of formulas? Seriously, by the end of this, you're going to have two incredibly simple tricks that will let you solve almost any problem. So let's just dive right in.
So, if you're studying for big exams like NEET or JEE, you know exactly what I'm talking about, right? Those endless lists of formulas for moment of inertia. It feels like for every single object and every possible axis, there's a brand new formula you've got to cram into your brain. It is completely overwhelming. All right, so before we get to the solution, the magic tricks, let's just quickly break down why this is such a monster of a problem for so many people. Let's just visualize what you're really up against. I mean, just look at this. You've got rings, you've got disks, spheres, and for each one of them, you need the formula for its geometric axis. A tangential one, a diametrical one. The list just goes on and on. It's no wonder it feels absolutely impossible to memorize all of this. Staring at a list like that, you'd be totally right to think, come on, there has to be a better way than just memorizing. And you're in luck, because there absolutely is. We're about to replace that entire nightmarish list with just two simple rules. So here it is, the core of the solution. We're going to take two really powerful theorems from physics, the parallel and perpendicular axis theorems, and boil them down into two super simple tricks that are going to do all the heavy lifting for you. And here they are. Meet your two new best friends. For any parallel axis, the trick is to simply add mr squared to whatever formula you're starting with. And for any perpendicular axis, the trick is even easier. Just divide by 2. That's it. I'm serious. Add mr squared for parallel, divide by 2 for perpendicular. Now, let's see how this actually works.
Okay, let's put these tricks to the test. We'll start with a classic physics problem, the thin ring, and just watch how we can build all of its key formulas using just our two little tricks and only one base formula that you need to know. First things first, you only need to remember one single starting point. For a thin ring, the moment of inertia about its geometric axis, the one going right through the center, perpendicular to its face, is mr squared. That's it. This is our foundation. Everything else is built from here.
So what about an axis that's still perpendicular, but it's passing through one end, or the edge of the ring? Well, that axis is parallel to our geometric axis, isn't it? So what's our trick for a parallel axis? You got it. Just add mr squared. So our base formula, mr squared, plus another mr squared gives us 2mr squared. Simple as that. Okay, next up, what about the diametrical axis? The one that slices right through the center but lies flat in the plane of the ring. Well, this axis is perpendicular to our original geometric axis. So we use our second trick, just divide by 2. We take our base formula, mr squared, divide by 2, and the answer is mr squared over 2. See? No memorization needed. And this is where it gets really cool, because we can build on our results. What about a tangential axis, one that just kisses the edge of the ring? Well, this axis is parallel to the diametrical axis we just found. So we take that result, mr squared over 2, and we use our parallel axis trick, add mr squared. This gives us our final formula, 3 over 2 mr squared. See how easy that was? We just came up with 3 new formulas from one single base formula and 2 simple rules. So let's try it with a disk and see how the pattern continues. It works just as beautifully.
Now, for the disk, the one and only formula you have to remember is for its geometric axis, and that is mr squared over 2. That's our new starting point. Everything else is going to flow from this.
All right, first challenge, an axis through the end of the disk. Just like with the ring, this new axis is parallel to our geometric axis. So we take our base formula, mr squared over 2, and we apply our trick. We add mr squared. The result? 3 over 2 mr squared. Next up, let's find the diametrical axis of the disk. This axis is perpendicular to our geometric axis. So what do? We take our starting formula, mr squared over 2, and we use the perpendicular trick. Divide by 2. That gives us mr squared over 4. And for our last case with the disk, the tangential axis, this one is parallel to the diametrical axis that we just figured out. So we take that result, mr squared over 4, use our parallel axis trick one more time, add mr squared, and there you have it, 5 over 4 mr squared. It's that systematic.
Now, these tricks are incredibly powerful. They really are. But they don't work for everything, and knowing when not to use them is just as important as knowing how. So listen up, because this part is crucial.
I'm putting this on the screen because it is the single most important warning. Do not apply these tricks to all objects. They are specifically designed for things like rings, disks, and spheres, basically circular or spherical objects whose formulas are based on the term mr squared. So a great question is, why can't we use this on, say, a thin rod? And the answer is right there in the formula. The moment of inertia for a rod is ml squared, not mr squared. Our tricks are all about adding or manipulating that mr squared term. If the base formula uses L for length instead of R for radius, our tricks just don't apply.
There's also one other oddball case you should probably just memorize, the solid cylinder, specifically for an axis that's parallel to its flat face, like the one shown here. The formula is unique. It has both R and L in it. It's mr squared over 4 plus ml squared over 12. This one's just an exception to our nice, simple rules.
Okay, we've covered a lot, but what's amazing is that it all boils down to a very, very manageable set of information. So let's bring everything we've figured out together into one clear summary. And here it is. This is the big payoff. From just 2 base formulas, one for the ring, one for the disk, and our 2 simple tricks, we have generated all 8 of these key formulas. This is the slide you're going to want to screenshot for your notes. This turns hours of painful memorization into a simple, logical process you can do in seconds. So we've totally unlocked a powerful method for getting the right answers fast. We've mastered the how, but that leaves us with one last really fascinating question. What's the deep physics behind why these theorems even work? Why do these simple tricks hold true? That is your next step to explore. Thanks so much for tuning in.